I will talk mostly about two papers from this past summer. It's this one in collaboration with Igor, Benjamin Sogard, and Edward Witten, and this other one with Ross Dempsey, Anna Maria Gluck, and Benjamin Sogard. Also mentioned some earlier work. I think all the authors are in the audience, so you can also ask them questions. Igor already mentioned 2D gauge theories, just to put things in perspective again and remind people. So to study non-abelian gauge theories in 4 dimensions, which is our goal, eventual goal, it is useful to get inspiration from more tractable models in 2 dimensions. And in 2 dimensions, we have the simplest gauge theory, non-abelian gauge theory, would be 2D Yang-Mills theory. So too simple, it has no particles. The next more complicated would be the 't Hooft model, which is Yang-Mills theory, plus a fundamental Dirac fermion, which was solved by 't Hooft at large n. And then the next more complicated one, which is the topic of this talk, will be adjoint QCD, so Yang-Mills theory, coupled to Majorana fermion in the adjoint representation. The adjoint representation is real, so we can take the fermion to be a Majorana fermion. This is the simplest theory that has dynamical degrees of freedom in the adjoint representation of the gauge group. What are these two? What are we hoping to learn? What are these 2D theories good for? Well, they're good playground for various things, ranging from numerical algorithms, for instance, in light cone quantization, lattice gauge theory, DMRG, to QFT ideas, such as non-invertible symmetries, anomalies, and others, and maybe even to quantum simulators, either analog quantum simulators or putting them on quantum computers. So in this talk, I want to do 2 things. One of them is, the first one is to give some updates on numerical studies of adjoint QCD. And the second one is to talk about, more in the spirit of new QFT ideas, to talk about the supersymmetry of this theory, the specific value of the fermion mass, which is a little peculiar in that it's not manifest in the classical Lagrangian. So I'll explain how that works. So adjoint QCD, just to review, Igor already mentioned this. So SUN gauge theory, 1 adjoint Majorana fermion. The Lagrangian density has the gauge kinetic term, the kinetic term for the fermion, and also the mass term. There's only one dimensionless parameter, which is m over G Yang-Mills. In 2 dimensions, the G Yang-Mills has units of mass. And so we have to study the theory for various values of this parameter, but we don't need to do all values because we can use an axial transformation where psi goes to gamma 5 psi. Gamma 5 I denote by, this is the chirality matrix. This kind of transformation leaves the first 2 terms invariant and changes the sign of the last term. So we can use this transformation to set m to be non-negative. And the interesting points are 2 values of m equals 0, and m over G Yang-Mills is equal to square root of n over 2 pi. That I'll mention. The second half of the talk will be about the supersymmetry occurs for this second value. So Igor already mentioned this, that so SUN has, because the Majorana fermion is not charged under the center of SUN, then the ZN center, there's a symmetry, there's a one-form global, ZN one-form global symmetry, and the states transform under it, and there are n flux tube sectors that are labeled by the anality of the electric field. The anality I'll denote it by P, so to create the pth flux tube sector, we can just put at infinity P fundamental quarks and P anti-fundamental quarks to create a flux tube where the electric field has this anality. The flux-tube vacuum in 2 dimensions, unlike in higher dimensions, in 2 dimensions, the flux-tube vacuum is Lorentz invariant. So we should study all these. Flux tubes as vacua of the theory. In terms of flux tubes, one can define precise confinement criterion, which is the theory confines if the area, if the fundamental Wilson loop obeys an area law, and in terms of this flux tubes, what this means is that the string tension, which is defined as the energy difference in the energy density in the p=1 flux tube sector and the p=0 flux tube sector, this is non-zero. So if this is string tension is non-zero, the theory confines. If the string tension vanishes, then the theory doesn't confine. And also brief review of the general features of things that Igor mentioned. So the surprising features are at m equals 0 and at m equals this other value that I mentioned. So at m equals 0, even though there are no all the dynamical degrees of freedom are massless in this case, there's a mass gap, and numerics show that the lowest fermion mass is this value in 't units, and the lowest boson mass has this other value. So this is obtained starting in the 90s using Lycon quantization from work of Igor and others. One way to see that the theory is gapped is to describe the deep IR of this theory. So by bosonizing the fermions, one can get this SON squared minus 1 level 1 model, and then gauging. So this is a gauge WCW model. So you have to divide it by SUN level n, and we can compute the central charge, the IR central charge, is the central charge of the free fermions minus the central charge of this current algebra in the denominator, and one can check that this is 0. So the theory is gap. The other surprising feature at m equals 0 is that the theory doesn't confine. So the Wilson loop, the fundamental Wilson loop, has a perimeter law suggested in the 90s, can also be understood from this coset, which has 2 to the n minus 1 degenerate vacua that are related by non-invertible symmetry. And this implies, so this is work of several people in the audience, and this implies that the energy density, energy densities are all equal in all the flux tube sectors. So in particular, it implies that the string tension vanishes. So this is the m equals 0 point, the surprising things about it, and m equals this particular value, g Yang-Mills times square root of n over 2 pi. The surprising thing is that this theory has supersymmetry, and I'll talk more about it later. Other values of the mass, well, there's still a mass gap, and there's confinement. These are not surprising things, but to study the precise spectrum or the string tension, that requires numerics. So this is a very brief review. So what will I do in this talk? I'll talk about some numerical progress on using tensor networks for finding the spectrum at small values of n. And also, in the second part, I'll give you some better understanding of the supersymmetry at this particular value of the mass. So that's the plan. So I'll start with the first one. So this theory has been studied numerically starting in the 90s using Lycon quantization. So initially it was a large n. Small n was only more recently. Now, the main issue with Lycon quantization, so initially it was discretized Lycon quantization, but then in this paper, sorry, I should have just said Lycon quantization here. There's other truncation methods. So, but the main issue with Lycon quantization is that the vacuum is trivial, and in particular, there are no flux tube sectors, at least in the way that Lycon quantization is implemented right now. You know, in Lycon quantization, we get some spectrum, and then the question is, if the theory has multiple vacua, then what spectrum does that spectrum correspond to? Which vacuum does it correspond to? And it was confusing for a while, but now I think I know the answer to this question. So if you want to know, I can tell you. So in any case, in order to study all the vacua, I would say we need other methods. And the best method so far, for at least for small values of n, I think is the Hamiltonian lattice gauge theory combined with infinite tensor networks. And this is what I want to briefly mention. So Hamiltonian lattice gauge theory, Igor already introduced it. So it discretizes only space, not time. So then we get a quantum mechanics problem with some Hamiltonian. So for our theory, what are the ingredients of this lattice model? Well, we have the fermions, so we're going to have lattice Majorana fermions on sites. So those are chi and A. N is the site index, A is the color index. They anti-commute unless they're on the same site and of the same color, in which case they square to 1. And then we have gauge variables on links, like in any gauge theory. So we have on every link, we have an SUN valued operator UN, and then we have the canonical conjugates. Because it's a non-abelian gauge theory, we have like the left acting and the right acting electric fields. And then one can write down lattice Hamiltonian. So this is just a discretization of the lattice of the continuum Hamiltonian. The first term here is a discretization of the electrostatic energy. This term here is a discretization of the fermion kinetic term, and this thing here is the discretization of the mass term. Like in any respectable gauge theory, this Hamiltonian should be supplemented by Gauss' law, which is that the discretized derivative of the electric field is equal to the charge density, which is now the charge on each site. It's a very, very interesting lattice model. It has, we studied a lot. It has, the one interesting thing about it is that it has analogs of anomalies from the continuum theory, but this is something that I'm not gonna talk about. So that's a lattice model. And now the question is, how do we, so in principle, all we have to do is to implement this on a computer and then diagonalize the Hamiltonian. So the question is, how do we do that? And as I said, we made some progress using tensor networks. So I want to explain at a high level what the main ideas are. People here are not, most people are not working on this topic, so I don't want to go into details, but I just want to explain roughly what the ideas are, what's new in what we did. So in general state in a quantum system, so if we have some degrees of freedom on some sites that are labeled by these S's, then the general state is described by a wave function, A. So that's a very, in general, it's a very high dimensional Hilbert space. But in certain cases, for example, if we have gap ground states, it's useful to make an ansatz that takes the form of a matrix product. So we have, instead of having a general wave function here, we write the wave function as a product of matrices. So for each S, we have a matrix, and then we take the product of the matrices, except for the first one and the last one, where we just have vectors. So this is the matrix product state ansatz. And then the idea is to find these tensors, using the variational principle, find these tensors, the tensors that minimize the expectation value of the Hamiltonian. Usually this will be a very good approximation. How do we compute the expectation value of the Hamiltonian? Well, it's useful to write down the Hamiltonian also as a product of tensor operators like this, so H1 times H2 times H3 and so on, with their own virtual indices. So these are virtual indices and these are physical indices with their own virtual indices contracted. So the size of the matrix corresponding to the matrices corresponding to Hamiltonian is not related to the size of the matrices corresponding to these tensors that describe the state. So this is the general picture of how to compute an expectation value of the Hamiltonian. So the lines here means contractions of indices. So the vertical bonds correspond to physical indices, these ones over here, and horizontal bonds correspond to virtual indices. And the matrix product operators, or any operators, so the matrix product operator is just, the Hamiltonian is just this operator here. It acts only on physical indices. There's a generalization of this construction that's going to be useful, which is that one can generalize this to a notion that's called symmetric matrix product states, where both the physical and the virtual Hilbert spaces, for which we have these indices, transform in representations of some symmetry group G. And in addition to that, all the tensors here, so the tensors for the states and the tensors for the operators, are invariant tensors of the group G. That's what the symmetric matrix product states means. This will be important in the next slide. And now tensor networks can be of finite size, so that would correspond to simulating a theory on an interval, or they can be of infinite size, which would be corresponding to simulating a theory that's on the real line. And there are efficient algorithms for both finite tensors and also infinite tensors. So this is the general setup. Now we want to use this for a gauge theory. So how do we use this for a gauge theory? There's two naive approaches that we're not going to use. These are the first things you might think about. So the first one would be, well, we have matter degrees of freedom and we have gauge degrees of freedom. We can keep the matter degrees of freedom and the gauge degrees of freedom together. So say some of our physical sites would correspond to matter degrees of freedom. Some of our physical sites would correspond to gauge degrees of freedom. The gauge degrees of freedom, so the Hilbert space is infinite dimensional, so that would need truncation. So that would be a downside of this approach. And then we would have to figure out what the gauge invariant states are. And that gets pretty complicated for non-abelian gauge theories. So for this reason, this would not be a very good approach for non-abelian gauge theories. And the other approach would be to solve the Gauss law. So if we're on an interval or on the line, in 1 + 1 dimension, then we can completely eliminate the gauge field. We can solve the Gauss law, and then rewrite the gauge kinetic terms in terms of the charges, but that would introduce non-local interactions. Maybe that's not that big of a problem. It's not that big of a problem if we have a tensor of finite extent, but if we have a tensor of infinite extent, that really would be a big problem. Because the only thing that we'd have to our advantage in that case, which is the translation invariance, would be broken by such a procedure. So we're not going to do that either.
I don't understand this.
Yeah.
Why is translation invariance broken?
Well, because we have to decide where to start solving from.
Non-manifest.
Not manifest. It would not. Translation invariance would not be manifest. Yeah, that would be maybe it wouldn't be, maybe broken is the wrong word. So not manifest. But that would mean, I mean, it really means that we can't. If these algorithms that exist for infinite tensor networks, we'd not be able to use them. So we'd like a setup where we'd have translation invariance.
I think there's a recent paper where they
Which case? In the shrinker. Yeah, so in abelian gauge theories, these problems can be overcome. They're harder to overcome in non-abelian gauge theories. Yeah, for abelian gauge theories, these are not that big a problem, but non-abelian gauge theories becomes bad. So anyway, the better approach that we found comes from the realization that these symmetric MPSs, where the Hilbert space is transformed in some representations of a group, which would be the gauge group, actually solve the Gauss law automatically. So the fact that the nodes are invariant tensors, this really is the local Gauss law condition, provided that on the physical Hilbert spaces, we put only the matter degrees of freedom and not the gauge degrees of freedom. And what that implies, so on the physical Hilbert spaces, we just have the matter degrees of freedom, and the invariant tensors solve the local Gauss law. So that implies, so these physical degrees of freedom here, these tensors solve the local Gauss law. So that means that on the links, we have information about the states of the gauge field. So then the question is, so the virtual Hilbert spaces, is the last point here, virtual Hilbert spaces carry information about the gauge field representations. So the question is then, how do we extract this information? Usually when we act with operators, we act only on the physical Hilbert spaces. We don't act on the virtual Hilbert spaces. So in order to read off the expectation value of this E squared term that appears in the Hamiltonian electric field density, we need operators that act on the links in order to be able to extract the representations. So in addition to regular operators that act only on the physical Hilbert spaces, we have to introduce some link operators that act on the links that can figure out from which we can extract the representations under the group G. And well, to our surprise, these kinds of operators had not been considered before. So for the gauge kinetic term, for instance, we would want these operators that act on the link to be proportional to the quadratic Casimir of the gauge group. So now these operators, the regular ones and the ones that act on the link, can be combined together. So this only works for symmetric MPSs, that we can have operators that can act on the links. So they can be combined together, and for symmetric MPSs, the most general operators are combinations of them. So before, from these ones, we could make a matrix product operator by having several of them and contracting the virtual indices in the horizontal direction. And now we can combine these with those and have a network like this, where we go from an operator that acts on a physical Hilbert space to the one that acts on the link, and then a physical Hilbert space, and then link, and then so on. So we called these operators link-enhanced matrix product operators, or LEMPOs. The nice thing about these operators is that they can be incorporated into existing codes, such as MPS kit code, which is a piece of software that's being developed actually across the street at the Flatiron Institute at CCQ, and we are very grateful for that. We can modify it to incorporate these operators. So that's the idea. Is just have some operators that can act on the links from which we can extract the information about the gauge field. So now there are efficient algorithms using for infinite tensors, as I said. So for infinite tensors, the idea is to have a state where I have some tensor A that's being repeated an infinite number of times, and then optimize over this tensor A. This is what the code does, to minimize the energy density, such that we optimize over A to minimize the energy density. There's some algorithms for this. So this is what we did. This is to find the ground state, but we can find the ground state in the P equals 0 flux tube sector, or we can find the ground state in any other flux tube sector. From taking the difference of the energy densities, we can then find the string tension. And this is how this plot was produced that Igor also showed in his talk. So this is the string tension for SU2 and SU3 adjoint QCD. Normalized, this is the string tension divided by the value that it would take in pure Yang-Mills theory. So that's why this, when the mass of as a function of mass of the fermion, when the mass of the fermion goes to infinity, this goes to 1. So this is sort of like, this kind of approach is sort of tailor-made for this kind of problem, because when we optimize over this tensor A, we really are minimizing the energy density, which is exactly the quantity that we need in order to compute the string tension. Yes?
Why does it get harder when you increase n? What?
It gets harder because the Hilbert space is bigger.
But it's all inside the gauge group. Is because number of representations grow, dimensions.
There's a number of representations.
So dimensions of your side, number of your legs is related to dimensionality of representations that contribute.
I think we'd probably need. There are several things that happen. Like we would need more representations, and also the representations get bigger. And one of the, I didn't describe the details of the lattice model, but in order to compute the expectation values, we'd need, for example, 6J symbols of the gauge group, and those become harder and harder to compute. So we have some results for SU4 as well, but it's very hard to go beyond SU4 with the brute force technique like this. From SU2 to SU3? Yeah, that's kind of surprising. So this is the string tension norm. Well, it's a little different, but not very different. So here it's in terms of the mass rescaled by g squared root of n. So if we didn't rescale by g squared of n, then of course the two curves would look different. What is blue? Blue is an analytical approximation at large mass. Large mass. So the leading order is just 1, and then one can compute corrections to that. Yeah, so it matches very well.
This model, the solid state mass is also approached large n already for n equal 2 almost.
Yeah, it's not the only quantity that doesn't have a strong dependence on n. Yeah, also the bound state, the masses of the lowest fermion and the lowest boson also don't depend in similar units. They don't depend much on n. Yeah, I should, as an aside, I should say that if the theory has multiple vacua, so for example, if we're in the trivial flux tube sector for larger n and we have several vacua there, then this procedure of optimizing over A actually finds several local minima corresponding to all those vacua, so one can actually study all those vacua that are related by non-invertible symmetry separately. So we've seen this in this example for SU4, and also there are several other gauge theories that we've studied. This is still work in progress, but hopefully it'll appear soon. So this is what Benjamin talked about in the Stony Brook conference.
0 when mass is 0, when you don't have these non-invertible symmetries on the lattice?
Well, so this is extrapolated to the continuum limit.
Oh, that's extrapolated.
Yeah. So I'm not plotting it at finite lattice spacing. I just extrapolate. Yeah, good. So we can do this, finite lattice spacing, and then we have to extrapolate to A goes to 0.
But at finite lattice spacing, even with 0 mass, you...
A finite lattice spacing, even at 0 mass, there would be a non-zero energy density. That's correct.
Okay.
Yes. Yeah. And the same would be true for different vacua in the same flux tube sector. But given though that's true, this minimization procedure can find all these vacua, which I find really, really neat. So this is just a ground state. To find the spectrum, one can form, it's called the quasi-particle ansatz. So we use the same tensor that we got from finding the vacuum, and then we change it at one point here, and then we sum over where we changed it. So we call this B with some weight, and then we create a state of some momentum, and then we optimize over B. This way we can find the low-lying spectrum. So I want to show you some plots of that for n equal 2 and n equal 3. So this is the first one. So this is n equal 2 in the trivial flux tube sector. This is the spectrum as a function of the mass. The fermions are in red, the bosons are in blue, and then the continuum, the two-particle continuum, multi-particle continuum is shaded. So you can see that at m equals 0, we start with like the lowest one is a fermion, and the next is a boson. These are the values that Igor also wrote on in his talk. And then as we change the mass, these masses change. At some point, which is the supersymmetric point, they cross all of them, and then they differ again. So this spectrum was obtained using the method that I mentioned. It also agrees with the spectrum that was obtained in Lycon quantization. But as I said, in Lycon quantization, one gets only one spectrum, and this is the spectrum that one gets. Now, this theory, the SU2 theory, has another flux tube sector, which is the p equal 1 flux tube sector. So one may wonder what's the spectrum in the p equal 1 flux tube sector. So we did that too. This is what it looks like. It starts at the same values at m equals 0, but now the masses go down, and the gap closes at precisely the point where we had degeneracy between bosons and fermions in the p equals 0 sector, and then becomes massive again. So why does this happen? Well, because at the supersymmetric mass, I showed you that the p equal 1 flux tube sector has non-zero vacuum energy density. That's the reason why the string tension, it was the string tension that was non-vanishing there. So this means that there's spontaneous supersymmetry breaking. So that means that in the p equal 1 sector, there's a massless Goldstino particle. And this is the lowest fermion here, this one, the red one, this is the Goldstino particle. It's close to this point, it's the Majorana fermion, whose mass goes to 0 precisely at this point. So I can wonder, okay, how does this look for SU3? This is SU3, we have a little less precision, it's harder. Again, we start with the values at m equals 0, and then, so this is a p equals 0 flux tube sector, and then the states cross at the supersymmetric point, and then they differ again. Again, so this p equals 0, this was also seen in Lycon quantization. You might wonder, okay, what is this? In this case, we have p equal 1 and p equal 2 flux tube sectors. By charge conjugation, they have the same spectrum. So we can find the spectrum in those sectors as well, and it looks like this. So again, we can see with a little less precision, but we see the gap closing precisely at this point. Yes. Continuum. Well, we see if we go higher in the spectrum, we'd see a bunch of states over here. These lines that we drew are based on adding the masses that the lower masses that we found. Yes.
Is the value of m SUSY predicted by the continuum?
The value of m SUSY is predicted by the continuum. Yeah,
so it exactly matches.
Yeah, this is what I'll talk about in the rest of the talk. Okay, so these are the updates on the spectrum. Now I want to move on to talking about the supersymmetry at this point, where m is Giang-Mills times square root of n over 2 pi. And supersymmetry was first noticed in Lycon quantization by Kutuzov in the 90s, who constructed two supercharges that square to the momentum generators. But as I said, there's some issues with Lycon quantization, so we would like to have a better explanation. Two relatively obvious things is that supersymmetry must be realized nonlinearly in this model because we only have dynamical fermions. And the other one is that it must be, something about it must be non-trivial because the action is not, as I said, the action is not invariant under any classical transformation rules. For the rest of the talk, just to clear what formulas I'm writing, I'm not going to work in Lycon quantization, but I'm going to use Lycon indices. So plus minus indices on vectors just mean V0 plus minus V1 over root 2. And for spinors, I'm going to use also chiral indices So I'm going to work in a basis where the chirality matrix is diagonal, sigma 3, and then the top one is going to be psi minus, and the bottom one is going to be psi plus. So, based on Lorentz transformation properties, or also, looking at the formulas from that Kutuzov had for the charges, one can guess some expression for the supercurrent. So these are the components of the supercurrent. The first index here is mu, the spacetime index, and the second one is the spinor index. So J minus minus would be trace psi minus cubed, which can also be written as trace psi minus J minus, where J minus is the minus component of the SUN current that's gauged, which is psi minus psi minus. And then J plus minus would be some number alpha that we might want to determine, times trace of psi plus F. Psi plus is the component of the fermion, and F is the field strength. So in 1 plus 1 dimension, the field strength is a scalar. So we can contract F mu nu and F with epsilon mu nu to get F, or we can think of F as being just F plus minus. And then we have the other two components, J plus plus and J minus plus, which are obtained from the top ones by flipping minuses to pluses and pluses to minuses. And then to find alpha, we should require conservation. So d mu J mu equals 0, which means in these light cone coordinates means d plus J minus plus d minus J plus for the spinor index minus is equal to 0, and a similar equation for the spinor index equal to plus. The second equation follows from the first one by parity, so just focus on the first one. So we have to compute two quantities, two derivatives. This derivative of J minus minus and the d minus derivative of J plus minus. For that, the equations of motion, the relevant equations of motion are the derivatives of the fermions. D plus of psi minus is proportional to psi plus, d minus of psi plus is proportional to psi minus, and d minus of F is J minus. There's a little bit of algebra. If we plug in the derivatives into the expressions for the currents, we find that the derivative d plus of J minus minus is proportional to trace psi plus psi minus, and d minus J plus is proportional. It has two terms now, one proportional to psi minus F, and the other one proportional to psi plus psi minus. So you can see that we want them to add up to 0. They won't be able to add up to 0. We could choose alpha such that these terms cancel, but this term, the first term, is not going to cancel. However, the subtlety is that product of fermions at coincident points is divergent. So if we expand the product of two fermion fields, the leading divergence is proportional to the unit operator, coefficient 1 over x minus. So a proper definition of trace of psi minus cubed would need regularization. What kind of regularization? Well, we can just take our 3 points. So we have 3 psi minuses. We can split them and insert small, in order to preserve gauge invariance, we should insert small Wilson lines between the 3 points, and this is the expression that's written here. And now it's some mechanism like the anomaly mechanism. It is an anomaly mechanism where if we take a derivative with respect to x plus, the derivative will receive some contribution from when it acts on the small Wilson line. Now, when the derivative acts on a small Wilson line, we're going to get a small contribution because the Wilson line is small. However, the product of the two fermions is large, goes like 1 over epsilon. So then we're going to get a finite contribution. One way to see this is in equal time quantization. If we separate the points in the spatial direction, we can see that even though this regularized version of trace, well, even though naively trace I minus cubed would not depend on the gauge field, actually because of the regularization, it does not commute with the electric field. So the commutator between this and the electric field, which comes from the commutator between the A and the electric field, would give something non-zero, and it gives something proportional to just a psi minus. And then that implies that the derivative of trace psi minus cubed, which we can compute by commutator with a Hamiltonian, is also receives an extra contribution. So in the end, there's one extra term in the derivative, d plus derivative of trace psi minus cubed, which is minus n over 4 pi trace psi minus f. So then I wrote down this expression here again. So the derivative of j minus minus has these two terms. This is the new term that we got from this regularization. You could also think of the extra term as coming from a Feynman diagram. It looks like this, where like there's two fermions that get turned into an F, and it's exactly the same diagram that one would compute if one were to study the axial anomaly. It's actually the same, so it's the same diagram as for the axial anomaly, it's just applied to a different operator. So now that we have two terms here, in the other derivative of d minus j plus minus, we also had two terms, and we can then make them add up to 0 by choosing m and alpha appropriately, and supercurrent is conserved if m is exactly this supersymmetric value, and alpha is given by this expression. So that's how it works. We can check that the supercurrent and the supersymmetric theory should belong to a supermultiplet. So we can check that the supercurrent belongs to the same multiplet as the stress tensor. In 1 + 1 dimension, the multiplet contains another scalar operator. Anyway, using all this technology, we can check the various commutation relations. So commutation relations between same chirality between the supercharge and the supercurrent give components of the stress tensor, and opposite chiralities, these give derivatives of this scalar z.
But in terms of particle, what is supermultiplet? Because you do not have gauge particles, right?
There are no gauge particles.
So it's singlet then.
So yes, so fermionic particles would be superpartnered. Their superpartners would be bosonic particles.
No, but there is no bosonic particles, right?
There are. We have two fermions, for example.
Yeah.
That's right.
So then it's supersymmetry between two fermions. So I mean, not just kind of normally, but you would say that it is fermion and boson, right? But there is no bosonic.
But there are bosonic particles that are just bound states of fermions. And those are the superpartners of the fermion.
I see.
And the reason why that happens is that the supersymmetry is realized nonlinearly.
I see.
So you can write down the supersymmetry transformation rule of psi, and psi would go to the current J, which is quadratic in psi.
I see.
Yeah.
So
Yeah.
this is very nice, but it's not the end of the story because it's not real axial shell. So let's say I gave you tomorrow a sextic operator and asked you, does it preserve supersymmetry? It would take you probably a lot of effort to compute.
It would take us some effort to compute.
So it would be nice to find an off-shell realization of supersymmetry. So we know what are the...
It would be nice to find an off-shell realization. Yeah, that's right. Yeah, I guess one other thing I can say about this is that one can also think about it from a path integral approach. And there one can write down some transformation rules. And you see that the action classically is not invariant. I have an extra slide at the end if you'd like to see it. And the non-invariance of the action is canceled by a factor that comes from the change in the measure, just like the usual anomaly. Okay. So so this is the story of supersymmetry in our better understanding now of supersymmetry in the adjoint QCD theory. So for the rest of the talk, I wanted to talk about the generalization of this construction, unless there are other questions. Okay, so one can generalize this to a larger class of theories that were studied by Fedor in 2022, where we start with our adjoint QCD theory, so gauge field and Majorana fermion with some mass, and to that we add some massless fermions. So I wrote here the massless fermions as if they're complex. If they're real, we can just put a 1/2 in front of the kinetic term. So in this case, the total gauge current has a contribution from the adjoint fermions, which is I'll call J. So J is just psi bar gamma mu psi, and also contribution, which I'll call J tilde from the massless fermions, Q. Now this J tilde forms so J forms a current algebra, SUN current algebra at level n, and J tilde forms an SUN current algebra at some level k that can be computed from the representation that these fermions transform in under SUN. So what's the physics that we expect Well, in general, for m equals 0, m not equal to 0, so the mass of the adjoint fermion not being equal to 0, which is where we expect that some value will have supersymmetry. If the adjoint fermion is massive, then we can just integrate it out, and then we just have the gauge field and these massless fermions. And in the d pi r, this is described by a coset CFT, which is SO dimension of R level 1 divided by the thing that's gauged, which is this SUN level K current algebra. And the central charge in the IR can be computed, and in general, it's given by, the formulas for this. In general, it's non-zero. So in this class of models, generically in the infrared, we have a non-trivial CFT. So again, we can guess the supercurrent. So I should say that Fedor found in light quantization, found the supercharges. So we can guess the other way. We can guess again the supercurrent. So it's the same expressions as before, except that J minus minus and J plus plus receive an additional contribution. This one proportional to psi minus times J tilde minus, which is the contribution from the contribution to the current from the massless fermions, and this one has J tilde plus instead of J tilde minus. And before, it was this term, the trace I minus cube, that required regularization by point splitting. And now it's also this term that will require regularization, second term that will require regularization by point splitting. So the analogous computation, I'm not going to go through it, gives that this current J mu is conserved if the mass is now a slightly different value. Very similar formula to the one before. The only difference is that instead of having square root of n over 2 pi, now we have square root of n plus k over 2 pi.
But before it was, G tilde was defined with, so which value of A or whatever is here.
Okay, I'm taking a trace.
Trace, yeah?
So I write it in the fundamental representation, say, and then I take the trace.
Sorry.
I multiply by psi and I take the trace. Or I just sum the color components and I divide by 2, whatever.
I missed, what was K?
K is the level of the current algebra that that J tilde has. So J tilde is the current of the massless fermions, and it forms a current algebra, SUN current algebra at level K. That's what K is. It can be determined in terms of the representation R that the fermions transform under. We find that the supercurrent is conserved, provided that M is given by this value, as I said, and this value agrees with what Fedor found. But there's a surprise. The surprise is that if we try to look at the supercurrent multiplet, and again, it has the supercurrent, a scalar operator, and a conserved stress tensor. And now if we were to compute the conserved stress tensor that's related by supersymmetry to the supercurrent, it actually isn't equal to the stress tensor that one would normally write down for this theory. So this theory actually has two conserved stress tensors, the actual stress tensor and the stress tensor that's in the supersymmetric multiplet. So the stress tensor in the supersymmetric stress tensor is this. I wrote down the formulas for it. It's a bit hard to see right away if you haven't done the computation. But this is exactly the formula that you'd write down for the full stress tensor, except that the contribution from the massless fermions to this stress tensor is replaced by a quartic term in the fermions proportional to trace J tilde squared over here and over here. So the contribution to the stress tensor from the Q's is replaced by these quartic fermion, which is quadratic, is replaced by these quartic fermion terms. Again, the quartic fermion terms trace J tilde squared. Again, this should be defined by gauge invariant point splitting. So this is what I said here. The QA contribution is replaced by the quartic terms. So then there's two stress tensors. There's this one and the usual stress tensor. So then there's a difference. So the full stress tensor is a supersymmetric stress tensor plus some difference, delta t, which is also a conserved stress tensor. So we found that this delta t is the contribution to the stress tensor that one would have from the massless fermions minus these quartic fermion terms. So now this expression depends on the gauge field in two ways. It depends on the gauge field in the covariant derivatives here in the first terms. And it also depends on the gauge field in a more subtle way through the regularization of the composite operator trace j tilde squared, because those have to be regularized by gauging variant point splitting. And it turns out that the two effects actually go away, cancel each other out. So if we were to compute the commutator between the electric field and this delta t, it actually gets 0. So this means that this delta t actually does not depend on the gauge field. So we can write down an expression for delta t by replacing the covariant derivative by a regular derivative and replacing this gauge invariant point splitting by just a normal order. So this delta t then is, as I said, the terms that we have. This is the stress tensor that one would have in just a free theory of the Qs, and then we subtract this quartic fermion terms, but with a normal order prescription. Now, what are we subtracting really is the Sugawara stress tensor of the J tilde. So that means that delta t really is the stress tensor of the SO mod SU coset. In general, this isn't supersymmetric. And now delta t SUSY is the stress tensor that we got in the stress tensor multiplet. And this is supersymmetric. So if the first one is the stress tensor of the CFT in the infrared, this is the stress tensor of whatever else is there, which is a massive sector. So in general, these theories have only partial supersymmetry. The massive sector is supersymmetric, but the CFT is not. So then the question is, can one have, so in general, partial supersymmetry, but is it possible to have examples where we have a theory of this type that's fully supersymmetric with additional massless fermions that's fully supersymmetric? Or in other words, can we cancel? Are there examples where we can cancel the quartic fermion terms? And the answer is yes. There's two possibilities. One of them is if this delta t actually vanishes, or in other words, if the coset of the would-be CFT actually has c equals 0. So in that case, the full theory is supersymmetric, and an example of that is SUN gauge theory with one massive adjoint and one massless adjoint. So now the Qs are just like one massless adjoint that produces a current algebra at level n. So then the mass for supersymmetry is Yang-Mills times, it usually was n plus k over 2 pi, and now it's n plus n over 2 pi. So this theory is fully supersymmetric. And another possibility to have full supersymmetry is if the CFT itself is supersymmetric. And that happens if we have SUN plus one massive adjoint, and then the Q fermions are two massless adjoints. And this generates a current algebra level 2n, and then this massive adjoint for supersymmetry would have to have mass Yang-Mills times n plus 2n over 2 pi. And the reason why this is supersymmetric is because this coset in this case, this SO 2n squared minus 2 level 1 mod SUN level 2n, has 2, 2 supersymmetry, and this is studied in this paper over here. So that's sort of what I wanted to say about this. Let me conclude. So the first part of the talk explains how infinite tensor networks and lempos allow for precise studies of the ground state and low-lying spectrum of adjoint QCD. Also generalizations, we're working on that. And in the second part of the talk, I explained another perspective on the supersymmetry of adjoint QCD at m equals this value, Yang-Mills times square root of n over 2 pi. And in this case, the supercurrent conservation requires a quantum anomaly. I should contrast that with the usual situation. The usual situation is that we have a theory which classically has some symmetry, and then because of quantum anomaly, at the quantum level, that symmetry is no longer, the current is no longer conserved. This is the opposite situation. In the classical level, the current is not conserved, but because of the anomaly at the quantum level, the current is conserved. And then there's a large class of theories with partial supersymmetry that are obtained from adjoint QCD by adding massless fermions. Didn't discuss many things, like more details about the lattice model, anomalies, tensor networks for other gauge theories, vacua related by non-invertible symmetry, strong coupling expansions, and so on. About the strong coupling expansion, I want to emphasize that I want to point out the fact that for these infinite tensor networks, the only parameter is the lattice spacing. So we don't have to send the number of lattice sites to infinity. We only have the lattice spacing. We only have to send the lattice spacing to 0 in order to go to the continuum limit. This kind of setup is exactly the setup that's usually used in the lattice strong coupling expansion. We're on an infinite lattice, and we compute as a function of the lattice spacing. So we can compare the results that we get from the infinite tensors directly with the lattice strong coupling expansion. In the future, I think it would be nice to think about scattering, either by setting up like some scattering states, or looking at time-dependent processes, and also looking at gauge theories in 2+1 dimensions in the Hamiltonian lattice approach. So thank you very much.